Any questions? The family. All right, so we're looking at assignment 6. Let me pull that up really quick here. And we're looking at you. Brianna, you're just like asking a little bit more about what that variable measures. Okay, so family technically is an identifier. It's just like saying 1, 2, 3. It's looking at our number of families. So it's not, I mean, it is sort of a variable, but it is an identifier. So do you think that means that it's very meaningful? Is it going to have any effect on our study? I would agree with that assessment, since it's just looking at kind of the idea of an identifier. Sure. Any other questions you guys have? Uh-huh. Okay. So when we think about interpreting the y-intercept, we're talking about when x is 0, what we would expect for our response variable. I'm trying to remember which study that is in the quiz. Go ahead. Sorry, say it again. No, so we are talking about a year of 0, because that's when x is 0. Okay, so it would be when our year is 0. So it is kind of strange, right? Because what would this be an example of? So is 0 the year 0 in our range of x values? Okay. Yeah, no, I agree. It's not in our range of x values. So we would call that in. Anybody can chime in. What do we call that if our x value is not in the range of our x values and we're trying to predict from that? Yep, that's an example of an extrapolation. Yep, it sounded good. Yep. Okay, any other questions? Oh, I'm seeing another one here. Just a second. I'm going to tell my kids to not stream. Explanatory variable. Yeah, explanatory variable would be the year for the quiz. Right. Everybody still hearing fine? I'm just going to probably periodically check in. Let me know if you can't hear or we're losing things. Cool. All right, so feel free to continue to ask questions as you have them, either through chat or through the unmuting and talking. I have been making videos of the notes rather than me trying to do notes while we work on this. I think that it's going to be better if I just make those video notes ahead of time. I'm also posting those keys so that you can kind of work through the notes, either watching the video or kind of using a combination of the video notes. The last video I did post is very long. It's like 30 minutes long. Feel free to fast forward through parts where you're like, I don't need to hear or talk about this. Or pause it if you need to write things down. I also would recommend, and that's kind of broke up. It's both notes for today. We won't have class technically on Friday. I will sit here for an hour. I'll be on my computer at 10 via Zoom, so you can check in and ask questions because we do have that assignment due that night. So I wanted to give you that opportunity to ask questions. But those videos are posted, and then it also covers information for class on Monday. So I did make a little kind of short worksheet over transformations and a couple other questions. So my kind of goal with these class sessions now is for us to work I'll post those videos of the notes, and then I'll make little short worksheets that we can kind of work through as a group. So I would recommend, if you can, that you guys work on those, print them off if you can, or have them on the side of your sheet or next to your computer, or however you want to work on them, or on your tablet, or however works best for you. And kind of work through those as we go. So now I kind of want to just back us up to Monday and look at the notes from Monday. And again, just kind of ask if there's any specific questions. I'm going to share my screen so you can see the notes. Again, let me know if you're having a hard time kind of seeing what we're doing, or if anything is not working. So are we able to kind of see the notes here? Can you guys see my shared notes? I'm not getting any feedback, so I just want to make sure that you guys can actually see my shared screen. All right, perfect, thank you. Okay, cool. Oh, I'm missing the chat. Okay. All right, so on Monday, pretty much the material that was covered in section 7.1 to 7.4 was over parametric and non-parametric tests and confidence intervals for simple linear regression. So some things we looked at is using R as a calculator to create a confidence interval. Just thinking about our basic idea of confidence intervals, it's showing us that we have our estimate plus or minus the multiplier, and we use a T-star multiplier with n minus 2 degrees of freedom. And then we're multiplying times the standard error of our estimate, whatever estimate we're looking at. So we can find confidence intervals both for the y-intercept. It's not really very useful to look at a test for the y-intercept because we're mostly looking about that relationship between x and y, that linear relationship between x and y. So we look more at the test of the slope. So we look at confidence intervals for slope and tests of slope. So any specific questions right now about confidence intervals for slope or testing of slope? Any questions? Okay. All right. So, and then we talked a little bit, in my notes, we talked a little bit about then interpreting slope. Some of that might have been reviews for some of you since we had already spent some time, in previous classes of interpreting slope. But interpreting slope for confidence intervals is a little different. So I'm just going to Oh, I want to point out the test statistic as well. I'm getting some errors, so let me know if you're not seeing something. The test statistic, we take our slope divided by the standard error of the slope. So we take our estimate of the slope, in this case, the 14.153, divided by the standard error, and that gives us this t value. Okay, so that's our test statistic here. Also, just kind of working through this, you can see how we calculated the confidence intervals. Notice that the 0.975 here, that references that 95%. So if we did a 0.95, we would see the confidence interval for a 90%. Seeing something in the chat here. Yeah, B1 is the estimate of the slope. So anytime we're finding either a confidence interval, that's going to be our estimated value for the slope, or if we're finding the test statistic. Answer your question, Stevie? Okay. All right. All right, so just there's a couple different ways to find confidence intervals. Remember, we can use the R code CONFINT, looking at our linear model, and we can get both the confidence interval for the intercept and for slope. So this is kind of a new idea here, thinking about interpretation of our confidence intervals. So we're not just saying that we're 95% confident, the values in between those, because we got to talk about our relationship between the two values. So here, when we're looking at the y-intercept interpretation of the confidence interval, we can say for an island with 0 soil types, we're 95% confident the true mean number of species, because that's what's varying, is our y, is between 7.39 and 280.43 species. And this is really going to kind of get important as we start talking about transformations as well. Thinking about confidence intervals too here for slope, interpreting confidence intervals for slope. We're talking about the change in x and how it's affecting y. So for each additional soil type, we're 95% confident the true change in mean number of species is between those two values, because we're talking about as x changes by 1, as it increases by 1, what's happening to our change in the response variable. Any questions? I'm not seeing anything. Okay. We then talked a little bit about permutation tests. So non-parametric tests, anytime we have evidence against normality and no influential points, we always want to think about using a permutation test or a non-parametric test for our simple linear regression. Of course, we'll need to look at diagnostic plots to determine that. So with our permutation test, we are permuting our values of slope. So we're looking at 1,000 different permutations of slope, assuming the null is true. And we're using that test statistic of our slope to find our p-value. So here we can see that the value of slope, the plus or minus value of slope, are way out in the tails of the histogram for our permutation test. So we are getting a very small p-value, less than 1 out of 1,000. Questions on the permutation test? I do go through some examples of interpretations and conclusions. So this conclusion is based on a test statistic, our value of slope, and a permutation test because we were using non-parametric methods and a small p-value. So just kind of thinking about those different things that we want to make sure we're including when we're talking about a conclusion. For our non-parametric confidence interval, we use bootstrapping. That's that process of sampling with replacement from the original data and then finding our confidence intervals by using the quantile or percentile method. And again, just finding that 95% confidence interval. Interpretations are the same when we think about a bootstrap confidence interval as for a parametric test. Any questions on our confidence intervals for slope or our test for slope, either non-parametric or parametric? Or interpretations of values? The red bars actually on the permutation test, that's representing where the test statistic falls, because that's for our test, not the confidence interval. So that's it was the value of slope. So 14.53 and greater gives us no observations, no permutations, and negative 14.53 and less is giving us no permutations. So we have a very small p-value. The blue lines are representing the confidence interval on the bootstrap distribution. Okay. Other questions? Okay, so that was like a really quick overview of our notes from Monday. So have any of you gotten a chance to look through the notes that I posted? I posted them later yesterday. But has anybody had a chance to kind of look at those transformation notes? Okay. All right, so I want to talk through, it looks like a lot of people haven't really had a chance, and I will be better about getting those out sooner. It was more just a decision yesterday that I think trying to do the notes real time is going to be kind of challenging. So I will continue to make those videos of the notes. So I'm going to go ahead and share that other set of notes with you. So these are the notes from section 7.5 and 7.6. I know it says section 2 at the beginning. That's just an error. So we can consider that that's not supposed to be there. So this is looking at types of transformation. So when we don't have a linear relationship between the explanatory variable and the response. So if we have some sort of curved relationship, then what can we do? So that's kind of what we're looking at with transformations. So it's probably going to be easiest actually if you unmute to ask a question, because I can't always see the chat going. So if you want to ask a question, just unmute yourself and go ahead and ask. So when we're looking at the transformations, the best way to look at, or the most common transformation, we'll say, is the logarithmic transformation. We do always call it log, but it is looking at a natural log, just so you know, so ln, instead of a log of different base. So it's just a natural log. So usually when we have transformations, the kind of the purpose is to be able to get a linear relationship between our explanatory and our response. So here you can see, kind of looking at before transformation, we have a right skewed distribution. After transformation, so they took the log of x, we're seeing a nice symmetric distribution. One thing that's important to note is our data has to be positive in order to do a log transformation, and it can't be 0. Also, tell me if I need to slow down. So we look at 3 different types of transformations, log transformations. We look at a log transformation of just the response variable. And then we'll also look at transformations of the explanatory and transformations of both variables. So a good time to use a log transformation, is when we have a skewed distribution. So here we can see voltage is fairly symmetric, but our response variable breakdown time is skewed to the right. So one important thing to note is when you create your R code, you're gonna just put in log of which other variable that you're taking the log of. So here we're looking at just the log of the response. So we're taking log Y distributed by our X variable of voltage. We get our estimates the same way. We could also, if we did a test, we can use that same T value. This would show the test statistic, the negative 8.84, would show the test statistic for testing the slope. And again, we can see a small p value here, but just so you know that basically you're looking at the same kind of tests. And so our estimated regression line, we're looking at the expected log of time equals our y-intercept of 18.96 minus the slope times the voltage. Any questions so far? Probably one of the hardest things to think about is the interpretations. One important thing to note is you really don't need to understand the math here. This is basically looking at how we would interpret our slope. We'll talk about both on the transform scale and then on the original scale. So when we talk about an interpretation on the original scale, we do need to think about back transforming. So that's essentially what this math is showing, is how to back transform the data. So what you need to know is you need to be able to identify, when you look at a test, you need to be able to identify what variable has been transformed and then how to back transform so that you can interpret the slope. Okay, so there's a couple ways to look at that. Good question. We can look in our R output up here. Since I can see that we're using the log of time here, I know that it's my response variable that has been transformed. So that's going to tell me which variable I have to back transform to talk about my interpretation. Otherwise, we might say that they took the log transformation of the response, or they took the log transformation of both variables, and that's kind of how you would know. Did it answer your question, Katie? Perfect. Any other questions? Yes. So I already posted the recording of me doing this set of notes. I will also post what I'm doing right now. I'm recording you guys. Right now we're not seeing pictures, at least, I guess, but I don't know, maybe my picture. I haven't recorded yet doing this, so. All right. So no, we would never make you do it by hand. It is going to just using the R code. You just take the log of that response variable distributed. So you're looking at the linear model of the log of Y distributed via X, R explanatory. Basically what R is going to do is it's going to take the log of every one of the y variables. So if you had a value of 1, it's going to take the log of 1. If your next value is 6, it's going to take the log of 6. So it's taking the log of each of the observations in y and plotting those against our explanatory variable. Did that answer your question? Nope, this is just scenario 1. So right now we're just talking about only taking the log of the response. Okay. All right, so when we interpret on the transform scale, essentially it's kind of the same as what we would do if we hadn't done any transformation. So you can see that it's just talking about an increase in X for a 1 kilovolt increase in voltage. We expect a negative 0.51, that's my slope, log per minute change in the mean breakdown time. Because we're talking about our change in 1 unit change in X, we're expecting our Y value to change by the slope. But when we think about interpreting slope on the original scale, we do have to back transform. So that's where we're going to take for when we have the log of the response variable transformation, we take e to the slope. So e to the power of negative 0.51. You can do this calculation in R, and that gives me a 0.6 value. So we know for a 1 kilovolt increase in voltage for a 1 unit change in X, we expect a multiplicative change, because that's what we see when we're looking at an transformation of the response in median breakdown time. So we talk about the median when we have transformed the response. You can kind of read through the notes from the book to give you a little better understanding of why we're talking about the median. He does a good job of explaining that. So it's a multiplicable change in median breakdown time, that's my Y variable, of 0.6. Questions on that interpretation? When we're asking for interpretations, we might ask you to interpret slope on the transform scale or the log scale, and that would be this right here. This is the just kind of normal way we would think about interpreting slope. If we ask you to interpret on the original scale, you have to do that process of back transformation. Any questions? Okay, we'll move on to thinking about transforming the explanatory variable. So again, this is looking at so now we're looking at a different study too. It's looking at meat processing. I didn't really talk about the study last time. So we're looking at pH in steer carcass, and we're looking at changes in pH. So we're looking at time as our explanatory variable, and the pH is our response. So here in this study, we're just going to transform the explanatory variable. So we can see that that explanatory variable time is right skewed. We might argue that there's a little bit of skewness here with our pH as well, but in this question or in this example, we're only going to transform the explanatory. So again, you can kind of just see it in the R output because our Y variable is not being transformed, but the explanatory is. Again, you find your estimated regression line the same way. You've got your y-intercept and your slope. Because we're transforming the explanatory, we're taking our slope times the log of time. So again, just thinking about those interpretations, when we use a log transformation of the explanatory variable, we're looking at when we double, we're basically saying that for a doubling in X, we expect a slope times log 2 change in the mean of Y. So we're talking again about the mean here because we're not transforming the response variable. So we don't talk about the median unless we have transformed the response. So again, on the transform scale, our interpretation just talks about for a change in 1 unit change in X, what's happening to Y. Since our X variable has been transformed, log transformed, we're going to say for a 1 log hour increase in time, because we're not talking about 1 hour increase, we're talking about 1 log hour increase. We expect a slope negative 0.54 change in the mean pH. On the original scale, we'd have to do that back transformation. So we're taking the value of slope times the natural log of 2, and that's negative 0.37. So for a doubling of time, my X value, we expect a negative 0.37 change in the mean pH. Questions on transformation of the explanatory? So we're going to use the words mean of the Y variable when we transform only the explanatory. When we transform the response, so when we take the log of the response variable, we're going to be talking about the median of the response. Okay. Other questions? I feel like I hear somebody else talking, but I can't hear you. Does somebody else have a question? Okay. All right. Is there a question? I mean, it might just be background noise, but I just want to make sure that I'm not missing somebody. Okay. All right, so the last transformation we'll talk about is a log-log transformation. So we're taking the log of both the explanatory variable and the response. So this is looking at the relationship between area of an island, like what's the square area of an island, and the number of animal and plant species living on them. So we're looking at the relationship between those. Here we can see that both of these distributions are skewed. So it makes sense to take a log transformation of both the response variable species and the explanatory variable area. Again, you find your estimated line of regression the same way. So you can see though that I put in log of species for Y and log of area for X. So when we back transform here for a transformation of both of our variables, when we talk about our interpretation of slope on the original scale, we're talking about for a doubling of X, we expect a 2 to the power of slope multiplicative change in the median response. So notice now we have the word median again because we're talking about a transformation, a log transformation of Y. So here on our transform scale, for a 1 log square mile increase in area, again, because we're just talking about an increase of 1 in X, but because we've taken the log, we need to talk about it about a 1 log square mile increase. We expect an average change of 0.25 log count in the number of species. So we're looking at that change in the log count number of species. On the original scale, we have to do the back transformation. So we take 2 to the power of slope, and that's a value of 1.19. So for a doubling of area, our X value, we expect a 1.19 multiplicative change in the median, because we have our transformed response number of species. Questions on those interpretations of transformations? Okay, so one thing I'd like to do now, we have a little bit more time here before I have to teach my next class. So I would kind of like to take some time and look at that that note sheet, or sorry, it's it says transformation practice for March 25th. Is everybody able to find that on D2L? It's under in-class worksheets, if that helps. And I can project it, but I was kind of wondering, and this is kind of up to you guys, so you can weigh in either by unmuting or chat. If you'd like to work in groups, I can put you in breakout rooms, and you can kind of talk to each other, like in smaller groups of like 3 or 4. It will be random, so I can't guarantee who you'd be with. Or we can just kind of keep the whole chat open, and you can kind of just work through the questions. So I'd love to see some weigh in here on whether or not you'd like to do a breakout room where you'd be in a smaller group and I can travel around groups, or if you'd like to just stay in the main room. Okay, everybody likes the main room. All right, so we'll stick with the main room. So I will open up that, I'm going to share that worksheet, but I would ask that you kind of work on it. Maybe we'll go through the first little bit together, and then you guys can just ask questions as you get stuck. Does that sound good? All right, so a couple things to just kind of point out here. So this is a study in 1994 on factors that impacted adult Americans' income. So we have a study of 1,192 adult Americans. So remember, we're always using a T distribution with N minus 2 degrees of freedom. So our degrees of freedom for this study would be 1,190. So those Americans were asked how much money they can earn and their height. They recorded their height. So they're looking on using a model that predicted yearly earnings based on the height of an individual. All the R output is at the end of this study. So I'm going to go ahead and we can talk about, and this, Stevie, was a question that you were asking about from, I can't remember if it was the quiz or the assignment, but talking about the strength, direction, and form. So strength, we're looking at, is it weak? Is it moderate? Is it strong? Direction, positive or negative? And then form, is it linear or nonlinear? So let's kind of look at that scatter plot. And if a couple people would kind of weigh in, looking at this scatter plot, what do you think about those 3 ideas here? So is it linear? Is it positive or negative? And what about the strength? It's kind of weird. I'm not hearing anybody. It doesn't seem very linear. It's maybe a little bit linear. We do kind of have a pattern going on here, but I definitely say it's a weak relationship. Maybe slightly positive. We could kind of cheat and look down here. Is our slope positive or negative? Positive. What's the value of slope? Good, right here. So it does have a positive relationship. It is kind of a funky one. This is a good one to look at for a transformation. So we could say it is got a slightly positive, linear, weak relationship. Yes, either linear or nonlinear. And I'd say this has more of a linear relationship than nonlinear. All right, so we already came up with our slope here. What would be our estimated regression line here? what's the value? So we know this is our slope and this is our y-intercept. What's the explanatory variable in this study? Height is, yes, the explanatory. Oh, I meant to ask what's the response. So what's our response variable? Okay, so we'd have our estimated earnings equals a negative y-intercept. I'm going to run out of room here, plus our slope times the height. Is everybody following where that came from? That's, I think, your answer to question 2. Yes. Sorry about that. Yes, I will do that. I didn't even think about it. I will always do that. I can throw it up there really quick right now too. I think I have it saved as a Word. Well, actually, I'll do it right after class. How about that? I realize we just have 16 minutes or 6 minutes left, but I will get it up there. So why don't you guys work on a slope? Actually, I'll post it while you guys work on your slope interpretation of your slope. And ask questions as you have questions. Okay, I did get that Word document up there. Any questions on how to interpret the slope? Obviously, there's no transformation yet here, so we don't have to worry about original versus transform scale. So at this point, we're just talking about as x increases by 1, what do we expect to happen to the average y value? All right, I don't know where we're at here. You can stop me if you have questions. Looking at the diagnostic plots, do you think we have any issues with our assumptions? Yeah, well, it's actually right skewed because we don't have it in both tails. So this is definitely right skewed. So we definitely have evidence against normality of residuals. So a transformation probably would be fairly useful in this situation. We might also have some issues with constant variance. We can look at both this residuals versus fitted plot and the scale location plot, and we can kind of see that there's some variability in our constant variance, so we might also have some issues there. But we definitely have evidence against normality of residuals. How about any issues with leverage or influential points? Yes or no? No, we don't have any values with a Cook's distance greater than 0.5. So really the only one that shows a clear violation would be our normality of residuals. Like I said, we might have some issues with equal variance, but it's not a clear violation. Yep. So we have to look at the Cook's distance lines, so the red lines here, and this one doesn't show any values of greater than 0.05. I don't have anything pulled up that shows. So with those red lines, you would see a Cook's distance of greater than 0.05. This is showing the leverage of 0.006, but that's not a very large leverage either, so we probably don't have really any issues here. So if you kind of remember that we would have to see kind of these red lines in the Cook's distance, and they're labeled as like 0.5 or 1. We had another one out here of 1. And if we have values outside of those, then that we would call those influential points. Yeah, it's not showing any Cook's distance. Yeah. Correct. Okay. All right. So here they're telling you just to log transform the response variable. So which would be the appropriate equation for the estimated regression model? A, B, C, or D? For log, did you say B? Yeah, I agree, because we're looking at the log of earnings. That's our response. If we look down at the output down here, so this is the one that's showing the log of earning. We can see that y-intercept estimate and the slope estimate. So obviously it is now 10:50, so we're out of time. I will post this, I'll give you a little bit to kind of work on this, but I'll post this key for this practice as well. And I'll also post this video from our class period. Do you guys feel like this worked a little better today? Awesome. So we'll kind of continue with the way that we're doing. Like I said, I won't have official class on Friday, but if you have any questions, feel free to join me on Zoom. Thank you. We'll see you guys later.